ME350 example problem for application of Fourier's law for a given temperature distribution. A brick wall with a specified thermal conductivity, thickness, and total surface area separates the inside of an oven from an exterior room at a specified air temperature as shown. Based on experimental data, while the oven is heating, the spatial change in temperature is mainly in the x direction only. For a given instant in time, a polynomial curve fit to the temperature data is given in dimensionless form as indicated. For this problem, for part A, find the rate of heat transfer into and out of the wall. For part B, find the rate of change of energy stored by the wall. And for part C, find the convection coefficient for the air in the room. Our first assumption for this problem is one-dimensional conduction in the x direction only, which is based on the information provided in the problem statement. Our second assumption is that there is no energy being generated in the wall, which is again based on the problem statement because it does not include any indication of internal heating. Our third assumption for this problem is negligible radiation for the exterior boundary. This is a reasonable assumption for an opaque wall and for lower temperatures combined with significant convection at the exterior boundary. For part A, to determine the rate of heat transfer into and out of the wall, we can use Fourier's law to calculate heat transfer rate by conduction from our known temperature distribution. From assumption 1, for the x direction only, Fourier's law can be written as shown. Substituting in the known temperature distribution, we get a function for the heat transfer rate at all locations in the wall. Next, to get the heat transfer rate into and out of the wall, we evaluate this function at the inner wall at x equals 0 and the outer wall at x equals L. Substituting in values, we get that 900 watts is entering the wall from the inner high temperature region and 100 watts is leaving the wall to the outer room air. For part B, to determine the rate of change of energy storage, we apply an energy balance to a control volume that includes the entire wall. By assumption 2, for no energy generation in the wall and for conduction only in the x direction, our equation reduces to the change in energy storage in the wall is equal to the difference between the rate at which energy goes into and out of the wall. Substituting in numbers, we find that at this instant, 800 watts of thermal energy is being deposited in the wall. For part C, to determine the convection coefficient for the room air, we now apply an energy balance to an infinitely thin control volume at the surface at x equals L. For this case, where the control volume has no mass, our energy balance reduces to the rate at which energy goes into and out of the control volume must be the same. For the energy in, we can use our result for the conduction in the wall at x equals L. For the energy out, in general, there will be convection to the air and radiation to the surroundings. From assumption 3, we assume that the radiation is negligible and we substitute in Newton's law of cooling for the convection. The resulting equation can be solved to obtain the convection coefficient from the specified conditions. Substituting in values, we get 10 watts per meter squared Kelvin, which corresponds to a typical value for natural convection to air. As an additional note, I'm going to describe where the temperature distribution we use for this problem came from. In particular, I used a numerical method to solve the heat diffusion equation, which is a differential form of conservation energy for conduction problems for the specified parameters. Note that the boundary condition at x equals 0 is a constant heat flux from the high temperature region of 900 watts per meter squared, and the boundary condition at x equals L is convection to air at 20 degrees Celsius with a convection coefficient of 10 watts per meter squared Kelvin. The initial condition is that the wall is at the same temperature as the surrounding air, thus it is also at 20 degrees Celsius. The properties for the wall are for typical clay bricks. Using these conditions, I obtained the temperature distribution at a range of locations and times and used a polynomial curve fit to the results after 5 hours for this problem. Finally, here is a plot of the temperature versus X location, or temperature profiles, at a range of times. At the initial time, the temperature is uniform at 20 degrees Celsius. After 5 hours, the temperature is approximately 130 degrees Celsius and 30 degrees Celsius at x equals 0 and L respectively. A polynomial curve fit for the temperature at this time, which again is the one we use to solve this problem, is indicated by the asterisks and corresponds to the curve labeled fit. As time continues to increase, the temperature in the wall continues to increase and asymptotically approaches a steady-state distribution that is linear. Later in this class, we will learn how to solve for the steady-state distribution when we cover Chapter 3, and we will learn how to solve for the transient solution when we cover Chapter 5.